All right. Well, I think as the last people are coming in, I think I want to get going here. So we're going to be talking about mass spectrometry for probably the next three lectures. Today I'll sort of introduce mass spectrometry. We're going to, at all points, I think, really try to stay on top of concepts as well as details, because I think in the end there are just enough items that we're juggling around in order that it's a little tricky, because you're juggling the items of what's the charge of your molecule, how did it get charged, you're juggling what's the isotopic composition and the distinction between the molecular weights that you use for weighing out a mole of compound or a millimole of compound, and the exact masses, the isotopic masses. And then we're juggling, in some cases, concepts of fragmentation. And the way in which I teach mass spectrometry is a little bit different than Silverstein and most of the textbooks, and probably your undergraduate textbook. So most of the textbooks start with electron ionization mass spectrometry, which is sort of the historical approach, and then do short shrift to the more modern techniques. And we're going to start in the reverse and really start with the techniques that you're going to be using. So before we get going, I want to talk about the things that you can learn from mass spectrometry. So one of the most valuable things that you can learn is the molecular weight. But there's way more that you can get ideas about. You can figure out what elements are present. And this is something incredibly valuable, because there's nothing in NMR that's going to scream at you or talk to you that there's a sulfur in the molecule or a silicon in the molecule or a chlorine or a bromine in the molecule, the way that mass spectrometry was. You're also going to be able to learn, oh, there's a nitrogen in the molecule, or at least in some cases you will. So we're going to be learning about isotope patterns, and I'll briefly touch on the so-called nitrogen rule. Molecular formula is another thing that you can get that's very valuable. In some cases, it's just by deducing it from knowing, okay, we have this many carbons or this many hydrogens. But specifically, what's often referred to as high-resolution mass spectrometry, but perhaps is better described as high accuracy mass spec, or as I said, sometimes it's referred to as high resolution mass spec. This can give rise to unique molecular formulas that only match that highly accurately determined mass. Also, particularly in the case of biomolecules, you can get information on what the structure is from, in the case of small molecules and EI mass spec, the fragmentation pattern. But also from techniques like mass spec, where you deliberately fragment the molecule in biomolecular structures, particularly for peptides and proteins, where you basically can break the molecule amino acid by amino acid. And we're not really going to be focusing on biomolecular NMR. So if you are going to be doing proteomics, you'll want to be reading on your own about the techniques, because there's a whole bunch of sort of more specialized information, including things like triptych digests that come into play. All right, so I want to start with something very fundamental, and I think it's easy to lose track of the fundamentals because we're trying to keep a bunch of ideas present in our head as we deal with mass spectra. So the very basic principle is that charged particles are deflected by an electric field, and moving charged particles are deflected by magnetic fields or electromagnetic fields. So I'm going to write this down. Now, the reason I'm writing this down is it's very easy to lose sight of the fact we need to get a charge. And of course, by particle, I mean molecule. So we need to get a charge onto our molecule. And doing so is going to alter, since most molecules are neutral, doing so is going to alter the properties of the molecule. It's going to alter the molecule. In short, you'll be applying a proton to the molecule or applying a sodium ion to the molecule. We also need to get it moving, and we need to get it moving in the gas phase, which in the case of big molecules means you have to get them into the gas phase, and I'll talk more about that in a moment. Now, there's also another principle. On the mass to charge ratio. And again, I'm going to put a little bit of emphasis on this. Again, I'm going to put a little bit of emphasis on this because it's not simply the mass that you're looking at. It is the ratio of mass to charge. And with larger molecules, where you may sometimes have more than one charge on the molecule, the peak that you're seeing is not the molecular weight or the molecular weight of the monoprotonated species. It may be the molecular weight of a diprotonated species, or the species with a proton and a sodium on it, or two sodium ions. Furthermore, the heavier the particle, the less deflection. And to a certain extent, that means that your technique becomes less sensitive for very high molecular weight. So in other words, if you're dealing with a protein that's 30 kilodaltons and you have one charge on it, what's needed to detect that is going to be very different than if you're dealing with a small molecule that has a molecular weight of 300. Fortunately, for something like a large protein, you're usually going to have multiple charges on it. And so, in turn, more charge leads to more deflection. And none of these ideas are hard on their own, but we're going to be keeping all of this in our head and more as we go on and just sort of treating it as background. Any questions or thought at this point?
By more charge, do you mean charged sites or net charge?
Net charge. So basically we are literally dealing with physics here. It doesn't matter where the charge is, it just is the physics of basically having a mass moving in a magnetic, having a charged mass moving in a magnetic or an electromagnetic field. Now, as with all of the techniques I talk about, I try to reduce the instrumentation to the bare bones because understanding sort of what's happening is key to knowing what's going on, and maybe the details become a little less important, although believe me, if you talk to Felix, or certainly if you talk to the former director of our mass spec facility, he would wax poetic about orbit traps versus quadrupoles versus ICR versus MALDI. But let's come down to the basics here so that at least we can get some understanding. So most organic molecules are going to be neutral. So the first thing that you need is to get a charge on the molecule through some ionization technique and get the molecule into the gas phase, usually at the same time. Then we need some sort of analysis technique. And what's going to come out of this is the mass to charge ratio, M to Z. And then you're off to interpret it. So for example, if you go ahead and do MALDI, and I should write this more neatly, MALDI top, you're getting the molecule into the gas phase and putting a charge on it by matrix-assisted laser desorption ionization. And then you're measuring how fast the molecule moves, which basically represents the acceleration across charged plates. So you're using, I'll say, plus time of flight analysis. And so in this technique, you're basically placing the molecule in a matrix in some organic compound that absorbs light, usually in the UV range. You're hitting it with a brief pulse of a laser. Often that's putting generally a proton on the molecule. Then the molecules are accelerated across charged plates. fly through essentially a tube, maybe back and forth with a deflector, come to a detector, and you literally, since the molecules are ions, you measure a current. You are literally detecting the electricity of those ions striking the plate, which generate a small electric signal. So basically now you'll get a time course of different ions coming in at different times, depending on how massive they are. Another technique that's very popular is electrospray ionization. In this technique, you're using a tiny little capillary tube that has a charge on it, and you're spraying your molecules in solution, and they're picking up charge, generally protons, sometimes sodium or potassium ions. And the solvent's evaporating, and the little droplets fly apart. You accelerate the molecules across a gap. And then often you will use this, I'll say often, with a quadrupole analyzer. And a quadrupole analyzer is basically 4 metal rods that have alternating electric fields on them, electric fields, alternating current on them, so that as the frequency of the alternating current is varied, different molecules can make it down to the detector at the end that picks up the electric signal, the electric current that they generate. So these are two of the contemporary popular techniques that are used, particularly for larger molecules. I'll tell you about other techniques in just a second, particularly older techniques. Thoughts or questions at this point? All right, so as I've been hinting, the ionization is often protonation. And so you can think of this as you have your molecule plus a proton, and you literally just protonate your molecule. And now the thing to keep in mind, okay, so we've put a proton on the molecule, and so the mass to charge ratio now equals the mass plus 1. So the peak in the case of a protonation, which you would get for MALDI-TOF or you would get for ESI, is typically going to be the mass plus 1, or more specifically, the mass plus 1.00783. I'll write that in parentheses here, since we will start to worry about that as we talk about high accuracy mass spec, but it's only going to be important then. But let's go ahead and keep from getting ourselves confused here. You can also, particularly in the case of larger molecules like peptides or proteins, pick up more than one proton. And so you can get M plus 2H, 2 plus. Now, our M to Z is not going to be M plus 1 or m plus 2, but it's going to be m plus 2 divided by 2. And so it's going to be twice the molecular weight, or more specifically, twice the exact mass, plus 1. Now, I also mentioned you could pick up a sodium. So you can pick up the sodium ion. And so if we're comfortable writing mass picking up, the molecule picking up a proton, we should also be able to be comfortable with the idea of it picking up a sodium. And you could write this as M plus Na plus. And then that's going to give us an M to Z of mass plus 23. Now, you look at this first and you might say, oh, that looks a little weird. But we're used to the idea of a proton, right? That's just a Bronsted acid. So it shouldn't be that weird that we can pick up a sodium, essentially a fat proton, as a Lewis acid on the same lone pair that we would typically pick it up. And you could also pick up potassium, K plus, and that's going to be 39 instead of 23. It's easier when we start to think about this in terms of some concrete examples and perhaps a little less confusing. So let's just take a carbonyl compound, and I'll just take this as R carbonyl R plus a proton, and we can easily picture a proton going on to the lone pair. If you like, you could even write curved arrows, but there's no particular need here. So it shouldn't be so hard to conceive of the same thing happening with the sodium ion. And certainly in your organic synthesis class, for those of you who take 204 or 205, you're going to see the idea of lithium going on to carbonyls as a Lewis acid. So again, not so weird, even if you haven't seen it in an earlier class. And of course, any lone pair is potentially a Lewis base. So if you have an ether in a molecule, you could go ahead and pick up a proton like so. As well, I think I'll circle my positive charge just to be nice here. Thoughts? Now, for modern instruments, the mode of ionization isn't only the positive ion mode. You can also have a negative ion mode. And so if we think about this as M minus H plus, in other words, loss of a proton, now we're going to get M minus H minus, and our M to Z is going to be the mass, not plus 1, but minus 1. what would be an example of this? Let's take a carboxylic acid, simplest example that you can think of. We have a carboxylic acid, we lose a proton, we get a carboxylate anion. Great way to ionize a carboxylic acid. So these are the techniques which many of you will be using, particularly for larger molecules, because in the case of larger molecules, it's hard to get them into the gas phase, and often the ionization techniques produce serious fragmentation. So in the course of your NMR studies, you'll be looking at strychnine as an example, which we'll be using. And for a molecule the size of strychnine, older ionization techniques often produce severe fragmentation and have trouble getting the molecule in the gas phase. But I want to take a moment now to introduce older ionization techniques. So one of the older ionization techniques is called chemical ionization. And chemical ionization is very similar to electrospray ionization, but you're heating the molecule to get it into the gas phase. So basically cooking it on a filament in a vacuum. And then you're going ahead and protonating it with a gas phase reagent. So I'm going to describe this as an older technique. And you do it as a gas phase reaction. With a reagent gas. And your Silverstein homework doesn't have, I think, any electrospray ionization or any MALDI-TOF in it. It only has electrical ionization, which we're going to see in a moment, and chemical ionization. And I want you to read, as you read Silverstein, and that's today's reading assignment, or maybe it was Friday's, but we're a little bit behind. As you read Silverstein, I want you to pay attention to the statement about how sometimes you will get the molecule combining with the reagent gas. Because at least on a couple of homework problems, you're going to see examples of this. So right now, I'm just going to write one of the popular reagent gases, which is methane. And it's so fun to be able to write this equation because we would all mark our sophomores off for writing what I'm about to write. So in the gas phase, one of the ionization gases that's used is methane. And in the gas phase, you can generate protonated methane, which should freak you out because you're basically sticking a proton onto the edge of the molecule, and you tell all your sophomores, no, you can't do that. But in the gas phase, that is generated and protonates your lone pair or just about anything for that matter. You can also use ammonia. It turns out the ammonium ion, NH4 plus, is also a very good acid in the gas phase. And then there are a few other ionization techniques as well, that a few other reagent gases as well. But the principles are very similar to electrospray ionization in the sense that you're generating a molecular ion that typically is +1 or sometimes has some additional thing on it. All right, now that brings me to our oldest ionization technique, electrical ionization. Electrical ionization is still very popular in the technique of GC mass spec, referred to as EI, not to be confused with ESI. And I'm going to describe it as an old technique and maybe I'll say it's especially good for nonpolar molecules. And I'll say it's also good for smaller molecules and those without polar functional groups. The reason I say this is you've again got to heat the molecule to get it into the gas phase. So you heat it on a filament in a vacuum, and then you bombard the molecule with electrons to knock out an electron. And once again, I'm going to mess with the inner sophomore in all of us by writing an equation and a structure that should mess you up. So let's start, and I'll write a molecule with a couple of lone pairs of electrons. So that could be a ketone or an ether, but honestly, we could also use an alkene or an arene that didn't have any lone pairs of electrons, or even an alkane, where instead of knocking an electron out of a lone pair, or instead of knocking it out of a pi molecular orbital, we're knocking it out of a sigma bond. So all of this should mess with you. So if we go ahead and take a molecule and give it a good hard whack with an electron fired from an electron gun or from an acceleration of electrons, we can knock out an electron from the molecule, leaving a positive charge. In other words, you take a neutral molecule, you take away one electron, that removes a minus charge, which leaves the molecule with a positive charge. And so to balance our equation, I'll say plus 2E minus. So this is what we would call a radical cation. Radical, of course, meaning it has an odd number of electrons. Cation meaning it has a positive charge on it. And since the mass of an electron is minuscule, it's a fraction of one mass unit, the mass to charge ratio is the same as the mass of the molecule. So just to put this into concrete terms, I'll take our hypothetical ketone and I'll take away an electron. And here's our radical cation.
question.
Yes.
How do we, for say, a plain vanilla alkane, how do you maintain a bond with the hydrogen if you're knocking out an electron to form the radical?
A great question. Okay, so let's, and again, you can muck with your sophomores for doing this. All right, so let's take the simplest of organic molecules, or one of the simplest of organic molecules. So let's take methane. And we're going to go ahead, we'll take away one electron from it. So that means we can think of there being 4 resonance structures that share the pane. To. So basically, if we want to think resonance structures, we're making do by delocalizing one fewer electron in the molecule. But it's certainly easier if you think about some sort of molecular orbital diagram and you imagine, okay, if here's our HOMO, right, and we have a bunch of filled orbitals and so forth, I'll just write etc. because I'm not paying attention. If you just imagine, okay, we've gone ahead, and again, I'll write etc. We've gone ahead and knocked an electron out of the HOMO and we're making do. Plain and simple. And what really is the killer, though, with EI is not only are you making do with fewer electrons, which might not be so bad in the case of, say, an ether where you're kicking it out of a non-bonding orbital, but you've heated the molecule and you've given it a good hard whack with an electron. So you've put in a lot of vibrational energy, which effectively is heating it. So you have a molecule that's already been weakened by the loss of electron, and it's high energy, it's hot. And so you get a lot of fragmentation, which can be very powerful in the sense that, and we'll use this, you'll use this in a couple of examples with ketones and other molecules. I think you'll get a fragmentation of a ketone where you'll figure out the structure in the homework. And I think you'll get a McLafferty rearrangement in the homework where you'll again use it to figure out the structure. But it can be confusing because sometimes the molecular ion is sometimes not seen. And that's confusing because then you'll think that the highest peak is the molecular weight, but the highest peak won't be the molecular weight, it'll be a fragment, and you'll get yourself confused. So sometimes you just see charge fragments. And this is, as I said, confusing. Now, your textbook has a way of helping you out. It'll help you out, but it'll confuse you as well. So often when you don't see the molecular ion they'll also use CI, which, as I said, is also an older soft ionization technique. Soft ionization basically is anything that doesn't give it a good hard whack with an electron and knock out an electron. And that often leads to less fragmentation. And as I said, your textbook, though, you'll get confused because often you'll see reactions with the reagent gas, such as picking up an allyl cation, and that can confuse you, but just read the textbook and you'll be prepared for it. ESI and MALDI, which are what I tend to use in my own group's research, give little or no fragmentation. And I guess I'd say, particularly with ESI, unless you want it, for techniques like mass spec, where you're deliberately selecting your ions and deliberately fragmenting them.
Dr. Nowick?
Yeah.
So you're saying that you use ESI mainly unless you actually want fragmentation?
In general, and certainly the mass spec facility now is set up very well for access to ESI and for MALDI. It's open access, and these are good modern instruments that you will get to use yourself in your research, and that's nice. So the cases where maybe these techniques wouldn't work so well is if you have a very big non-polar molecule with just no lone pairs of electrons. So for a molecule like anthracene, I'm not sure if you'd get a signal in ESI, or maybe you'd get a signal in MALDI, but it's harder to put a proton onto this. Molecule like anthracene would work very well with EI, or possibly CI, and part of that is the molecule can be roasted without decomposing it, whereas if you roast a peptide or roast strychnine, you're probably going to decompose it. But those are good ionization techniques for it. Also, if you're doing a small molecule project, you might end up using a technique like GC mass spec, and I'll mention a couple of so-called hyphenated mass spec, techniques. So who's done gas chromatography in the course of your research? So gas chromatography for small molecules is a wonderful technique because you separate them by basically boiling point and adherence, and well, more specifically by boiling point and adherence to a matrix, to a stationary medium, a liquid medium, and a column. But at that point, you've already gotten the molecule into the gas phase, which I mentioned is one of the sticking points for electrical ionization for EI. So GC mass spec works very well with electron ionization. It can also work with chemical ionization. And generally, if the molecule is stable enough to get it through a gas chromatograph, anthracene would be a good example, whereas strychnine would be a bad example. If the molecule, would not be a good example. If your molecule is stable enough to get it through a gas chromatograph, generally you're going to be able to go ahead and have it stable enough to get it ionized, even if it does fragment. The other hyphenated technique, which you will have good access to, and you have access to GC mass spec there, is LCMS, where you're running HPLC or UPLC coupled with mass spec. Your molecule's already in solution phase. And so I'm going to just write, this works well with EI and sometimes CI. And this works very well since it's already in solution. It works very well coupled with electrospray ionization because you basically just spray a small amount of your eluent through an electrical ionizer and evaporate the solvent and get it into EI mass spec. So that's another useful technique where you get sort of a second dimension, a chromatographic time dimension to separate your molecules. Anyway, so this is a collection of sort of basic techniques. And I think what I want to do, because in spite of the fact that this all sounds easy, or at least all sounds like the individual factoids I've been mentioning perhaps are quite accessible, I think what I'd like to do at this point is show a real spectrum here, and we can use this as a springboard for talking. All right, can you see my screen okay? And do you have the handout that I gave? All right, so this is an example of a peptide. And I think where I want to start, for starters maybe, is you're probably used to the idea of the molecular weight. And that's the composite weight. Your carbon is 1.1% C13 as well as 98.9% C12. So in this molecule with a formula of C39H64N6O4, some of your carbons may be C13. You may also have a little deuterium or nitrogen 15 or oxygen 17 or 18. But we're going to focus on what's called the exact mass. The exact mass is from the C12H1N14O16 isotopologues. In other words, the molecule where all the carbons are C13 and so forth. And so we see a series of peaks here. So for example, the exact mass is 744.5. And so to 1/10 of a mass unit resolution, in other words, we're off by a couple of tenths, we see at 745.7 or 745.5, I suppose it would really be, the M plus H peak. And if you look closely here, you'll see the C13. So this is with one C13, the isotopologue.
Dr. Nowick, can you move it up? I think it's blocking.
What's that?
Can you like scoot it up? I feel like it's blocking the part where you point out the C13.
Can you see now? Does that help?
Yes, that kind of helps.
Can you see the bottom of the scale? Can you see my cursor?
No.
No.
You zoomed out a little bit, James, but then it snapped back to where it was before. Do you have a way to permanently zoom out?
Does this help or no?
I think I have to move the mouse away from the bottom. Maybe that.
Does that help? Let me see. All right, I'm going to see if I can, All right, let's try this.
Move your zoom mouse from the bottom and go full screen, it's fine.
What's that?
Not you, I was talking to the person that asked. If you move your mouse from the zoom at the bottom and go full screen, you should be able to see the numbers at the bottom. I'm not sure if you're having that problem.
James, how are we doing now?
It looks, the same as before, but I agree with Parto's comment. If you are able to make the screen share into full screen and move your mouse away, it will get rid of the zoom bar at the bottom that has participants in chat that's blocking the scale. Otherwise, you could minimize the screen on your own page. Ah, I didn't know that shortcut. Okay, in chat, someone also mentioned you can just press the Alt button.
Ah, who's not okay at this point? I think what I'm going to do, because we're coming to the end of the class here, is I'm going to email this handout at the annotated handout at the end of the class for anybody who's had trouble. So we see another peak that's the biggest peak here. This peak is 22 higher. Instead of being at 745 and change, it's at 767 and change. This is the M plus sodium peak. Now we can clearly see the C13 isotopologue. So the peak that we're looking at 767.6 or thereabouts is all C12. But here we have one C13. And if you notice, if you peek right down here at the bottom, we see a peak where we see one additional peak where we have two C13s on it. So this is a little bit of an introduction to ESI mass spec. And you'll notice we see some lower peaks, and I talked about fragmentation. So this, for example, at 656.7 is a fragment, and this specifically is a fragment where this bond has broken, and now we've got our carbonyl as an acylium ion, and then we have our valine and our leucine, and so on and so forth. So that's a little bit of an introduction to looking at a real spectrum here. And as I said, I will plan to email this to everybody at the end of class so that if you weren't able to see it on the screen, you have it for your notes.